Hello, good evening everyone. As usual, we are continuing our weekly sessions for the course Machinery Fault Diagnosis and Signal Processing. So this week we'll focus on non-destructive testing basic techniques and some sample problems or sample questions regarding the topic. So let's begin the session. Today's first question is which of the following tests fall under the category of non-destructive testing? So, the options are acoustic emission, B. Ultrasonics, C. Vibration analysis, and D. All of the above. So, is acoustic emissions and ultrasonics and vibration analysis, are these non-destructive testings or destructive kind of testing? So, the acoustic emissions, ultrasonics, and vibration analysis, all these are non-destructive testings only, as you are not destroying the sample with which you are testing which you are using for testing. Like let's say if you are using a tensile test, then if you are using it till the breakage, then you are basically the sample is destroyed. So that is kind of destructive testing. And in acoustic emission and ultrasonics and vibration analysis, none of such destructions happens. So they fall under the category of non-destructive testing. So what are the other types of non-destructive testings that are available? Is radiography and eddy current based testing. There is dye penetration test. And there is thermography also, and magnetic particle inspection. So all these are examples of non-destructive testing, including acoustic emissions, ultrasonics, vibration analysis, radiography, eddy current testing, dye penetration testing, thermography, magnetic particle inspection. Okay. Yeah. So I hope this question is clear. These are some examples of the non-destructive testings. The answer is all of the above, actually. So let's move to the next question. So this question is regarding the ultrasonic techniques. So this question is for which kind of measurements you can actually use ultrasonic techniques. Can you measure the thickness using ultrasonic technique? Can you detect cracks? Can you inspect the weld job using ultrasonic techniques? You can actually do the thickness measurement. You can also detect the cracks. You can also do the weld inspection. So the answer is all of the above. So the ultrasonic techniques work like you have a transmitter or a transducer which generates sound signals, which generate sound signals, and they pass through the object, and some of the waves get reflected back. So you have a sensing system either on the back or front, based on the type of the material system and the testing technique. So you can either detect the reflected waves or the transmitted waves, and with the help of this you can actually measure the thickness, and you can detect cracks, and you can also do weld inspection. Because let's say if the sample is of certain thickness and there is a different sample of the higher thickness, the reflected waves from these two samples would be different. Similarly, a sample with a crack would have a different signature. So based on these different distinguishing features of the waves, you can identify the cracks and measure the thickness, and you can also do weld inspection. Okay. Let's move to the next question. Can ultrasonic technique can be used for ultra non-metallic materials? True or false? The ultrasonic technique can be used for non-metallic materials. It doesn't have to be any metal because you're not generating any current. It doesn't have to be conductive and all. So it's just based on the transmission of sound waves, and every material can sound waves can pass through every material. So ultrasonic technique can be applied for non-metallic materials, but there are certain categories of materials where ultrasonic technique is not that useful. Those are coarse grained materials. Fails for coarse grained materials. One example is cast iron. So if you want to detect a crack, so if there is a single crack, then you can detect it clearly using the ultrasonic technique. But if you have a coarse grained system, so with many edges like this, so all of this will create so much disturbance in the signal that you won't be able to identify a single crack. Okay, so that is why ultrasonic technique fails in coarse grained materials, but you can use it for non-metallic materials. Let's move to the next question. Which of the following characteristics of the defect can be determined using ultrasonic technique? Size, orientation, C, location. So which of the following characteristics of the defect can be determined using ultrasonic testing? So as I said before, the cracks have distinguished signatures in the reflected or transmitted sound waves. So based on the size, orientation, and location, whatever factors that can affect the transmitted or reflected sound waves, Those factors you can actually distinguish. So the size and orientation and location actually affects the transmitted sound waves or reflected sound waves. So you can identify all these features using the ultrasonic testing. But you need to do careful analysis, and you should first know what, let's say, a 5 mm crack size, how would the signal look like, or 6 mm crack size, how would the signal look like. So you should be able to distinguish between those two. But once you know that, you can actually get the size, orientation, and location from the ultrasonic testing. Okay, let's move to the next question. So can ultrasonic technique detect the sound beam cracks that are parallel to the propagation of the sound wave? So you have a system and your crack is exactly like this, and you're propagating the sound waves this way. So then you can't actually detect the crack. So in that case, the ultrasonic testing will fail. So usually you need to do it in multiple angles to see the presence of cracks, not just a single orientation. So yeah, ultrasonic testing, you can detect the cracks that are parallel to the sound beam because they might not reflect the sound waves. Let's move to the next question. Surface discontinuous will impact the effectiveness of the ultrasonic testing. True or false? So as we discussed earlier, the ultrasonic testing depends on the reflected or the transmitted waves. So let's say you have a crack, but you have the surface discontinuous like this. Then when a sound wave is coming, there will be some set of reflections from the discontinuous on the surface also and from the crack also. So there will be much more noise which will inhibit inhibit you from detecting the crack effectively. So surface discontinuous will actually impact the effectiveness of the ultrasonic testing. So this is one of the reasons why ultrasonics are bad for the cases of very complicated geometries, because each of these geometrical features will have a distinguished signal in the reflected waves. So you need to be able to differentiate them. So it actually becomes more and more complicated if you have a more and more complicated geometries. Okay, let's move to the next question. The purpose of the dye penetration test is to measure the thickness or detect the surface cracks, to measure the temperature or to measure the chemical composition or to identify the chemical composition. So the dye penetration test is actually to detect the surface cracks and not temperature or chemical composition or thickness. And the way it works is, let's say you have a sample, and if there are any surface cracks, and when you have dye with liquid on that, so because of the capillary action, so when you have very thin channels and if you are sending in liquid, so because of the capillary action the liquid can actually flow even without any external pumping. So because of that the cracks will be filled with the dye, and you can kind of estimate the size of the cracks uh, and see if there is any crack also. So dye penetration test actually works on the principle of capillary action and is used for the surface crack detections. Okay. Okay. So now let's move on to the next question. So these questions are now related to the eddy current based testing. So when you have a sample in a changing magnetic field, it generates eddy currents. And how does the density of these eddy currents change with the depth of the sample? So the eddy currents which work on the principle of magnetic induction. So a changing magnetic field will generate a current in a sample in a metallic materials. Now this eddy currents, so let's say you have a sample, so they actually vary exponentially with the depth. So at the surface you have very maximum intensity or density of the eddy currents, and as you move through the depth the density decreases exponentially. Okay. uh, yeah. So the eddy currents decreases exponentially with the depth. of the material. It's not linear and not uniform. Okay, now let's move to the next question. Skin depth of eddy currents increase with increase in conductivity. A to be false. So how does the skin depth of eddy currents increase with increase in conductivity of the sample? So as we saw in the previous question, the density of the eddy currents varies with the depth exponentially. So as it is varying with the depth exponentially, so the depth at which the density reaches 1 by E of the density at the surface. So that is called the skin depth. Okay. So if you have a material which is more conductive, the eddy current drops much faster. So it will have a lower skin depth. So the answer, eddy current increases with increasing conductivity, is false. So the skin depth is actually inversely proportional to the conductivity and inversely proportional to the permeability of the material, and it is also actually inversely proportional to the frequency of the changing magnetic fields. Okay, so the skin depth is the depth at which the density of the eddy currents reaches 1 by E of the density at the surface, and if the conductivity or permeability of the sample increases, the skin depth actually decreases. So if the material is high conductive, more conductive, or permeable. Okay, so let's move to the next question. Yeah. So as we have seen in the earlier question, we know how skin depth depends on the conductivity, permeability, and the frequencies. It's inversely proportional to all of them. Now in this question, what we are asking is, we know the conductivity of the material, we know the permeability, we know the frequencies. So can you estimate the skin depth based on these properties? Skin depth of the given material. So skin depth we can actually estimate from these properties by using this formula. So this is the conductivity in percentage ISES. So this is an international standard where materials are compared with the copper, I think, in terms of conductivity. P is the permeability in H per mm, and F is the frequency in hertz. Okay, and pi is the constant. So if you substitute the values which are given, pi is 3.14, frequency is 318 hertz, and p is 0.401, so 10 power minus 5 into percentage ISES is 100. Okay, so this would actually turn out to be 1 mm. Okay, skin depth SD in this case is 1 mm. So this is how you can estimate skin depth for a given material if you know the conductivity and magnetic permeability and the frequency of the eddy current source. Okay, now let's move to the next question. Materials under stress give out sound waves in the order of 20 megahertz or higher. Materials under stress give out sound waves in the order of 20 megahertz or higher. So this is acoustic emission. Uh, so materials under stress actually give out sound waves in the order of actually 2 megahertz or higher and not 20 megahertz. So the answer is false. So they give out in the order of 2 megahertz or higher. Okay, now let's move to the next question. Yeah. In the acoustic emission based technique, the source of the internal defect is estimated through which technique? So you can estimate the source of the sound wave using the triangulation technique and not FFT analysis, and you can actually determine it through triangulation. So it is similar to how a GPS location can be found by using the satellites. It is also similar. Its triangulation principle is used to detect the source of the internal defect. So let's move to the next question. So what are the types of acoustic emission signals? Either will they be continuous or will they be transient, or like signal, sudden signal and then nothing and again sudden, transient or continuous, like there is one amplitude or continuously, or both of them are possible or none. So the acoustic signals can actually be continuous or transient. So the answer is both A and B. It doesn't have to be either only one. It is possible for both type of acoustic emission signals to be available. Let's move to the next question. So this question is how to estimate the Q factor, saying you know the natural frequency and you know the frequencies on either side of the peak at which amplitude is 0.707 times the maximum amplitude. So let's draw the so this is the frequency at which frequency amplitude is maximum f naught. So this is the natural frequency, and on either sides where the amplitude is 0.70 times s. So this is f1 and this is f2. So the Q factor is related to such a frequency spectrum as f naught by f2 minus f1. So this is how we can estimate the Q factor. So in this case f naught is 100 Hertz and the difference between the two frequencies is 4 Hertz. So the Q factor is 25. Okay. So this is how we can estimate the Q factor from the frequency spectrum of a given material in the natural frequencies and the values at either side of the peak. Okay, let's move to the next question. What is the damping factor for the above case? So we have estimated the Q factor and we know the natural frequencies and the frequencies at which the amplitude is 0.707 times the maximum amplitude. Can we estimate the damping factor? So are damping factor and Q factor related? Yes. So Q factor is in terms of damping factor 1 by 2 zeta. So zeta is the damping factor. So now as you know Q factor, the damping factor is simply so 1 by 2 into 25. This gives us the damping factor. Okay. So let's move to the next question. Natural frequency of a system can be determined using the bank test. True or false? Answer is true. When you are actually doing a bank test, you are exciting the material at so many frequencies. So the maximum amplitude will be at the natural frequencies. So you can actually estimate the natural frequency of a system using the bank test. Okay, let's move to the next question. During bank testing, the system is excited at a wide range of frequencies. True or false? Answer is true. During bank testing, the system is actually excited at a wide range of frequencies. So that's how you can actually estimate the natural frequencies, because the amplitude at the natural frequency will be the maximum. Measurement of response as well as force is required in experimental model analysis. True or false? So response is usually based in terms of displacements or vibrations and the force. So in actual experimental model analysis, you actually measure both. So the answer is true. So both displacements or vibrations and force are measured in experimental model analysis. Inverse of mechanical impedance is called mobility, compliance, stiffness, resilience. So inverse of mechanical impedance is actually called mobility, and compliance is actually force displacement for given force, the ratio of displacement and the force. And stiffness is the opposite of that, it's force versus displacement. So the compliance is displacement versus force, and stiffness is force versus displacement, the opposites. And for the opposite of mechanical impedance is mobility. Okay. In vibrating structures, node points have a displacement equal to 0, maximum average decantation. In vibrating structures, the node points have a displacement equal to. So let's say this is the vibrating signal. So this is the point where the displacement is 0. So such points are called the node points and not the maximum or the average. So node points will have a displacement of 0. Instrumented hammer used in experimental model analysis usually has. Instrumented hammer used in experimental model analysis usually has. The instrumented hammer usually only has a force transducer. It doesn't have a vibration transducer. So you can only measure the force using the instrumented hammer. Let's move to the next question. In X-ray tomography or radiography, sorry, X-ray radiography, the intensity of the transmitted beam is related to the density as directly proportional, inversely proportional, not related. So it is actually inversely proportional to the density, and that is why you can actually measure the bones differently from muscles in when you do an X-ray, because if it's more dense, then the transmitted beam will have lower magnitude, so it becomes dark, and the system with very low density will be much brighter. So this is how you can measure the or you can identify the dense and low dense regions and any defects or anything. So in X-ray tomography, the density of transmitted beam is related to the density as inversely proportional. Okay, so this is the last question for today. I'll just revise once all the questions and then we can close the session. So what are the following tops? Which of the following are the types of non-destructive testing? Acoustic emission, ultrasonics, vibration analysis, radiography, eddy current testing, dye penetration test, thermography, magnetic particle inspection. All of these fall under the category of non-destructive testings. And select the applications for the ultrasonic technique. You can actually measure the thickness, you can detect cracks, and you can also do weld inspection using the ultrasonic techniques. Which of the following non-metallic materials or can ultrasonic technique be applied for non-metallic materials? Yes, it is true, but you can't apply it for coarse grained materials, for example, cast iron, because the cracks, the special signature of the cracks could be overlapped with the edges of the grain boundaries of the grains, so it will be difficult to actually see the cracks in a coarse grained material. But it can actually be used for non-metallic materials because you are not inducing any current or it doesn't have to be conductive, so you can use for any non-metallic materials. Which of the following characteristics of the defect can be measured using ultrasonic testing? You can actually measure the size, orientation, and location. All these three you can actually characterize using the ultrasonic testing. And if the crack is parallel to the sound beam, then such cracks could not be identified using the ultrasonic techniques. And if there are any surface discontinuities, they will create special signals which will create much more noise for the detection of the crack. So that is why when you have very complicated geometries, ultrasonics might be a bad option to detect the cracks in a very complicated geometries. In the dye penetration test, because of the capillary action, the dye can actually seep into the cracks, which are then usually at the surface, where you can reach with the help of a dye. And this works because of the capillary action. And the dye penetration test can be used for only surface crack detection. And the density of the eddy currents generated in any material actually decrease exponentially with the depth. And these eddy currents are usually generated when a connective material is in the changing magnetic field. And because it varies exponentially, there is something called skin depth, which is defined as the depth at which the density of the eddy currents drops to 1 by E of the value at the surface. And if the material is more conductive, the eddy currents drop much faster, so the skin depth is actually lower. So the skin depth is inversely proportional to the conductivity and permeability of the material. It is also inversely proportional to the frequency of the source, the magnetic changing magnetic fields. So you can actually estimate skin depth as a function of the frequency, permeability, and the conductivity as 1 by square root of pi f pk, where k is the conductivity in ISES, percentage ISES, p is the permeability in h per mm, and frequency is hertz. And materials which are under stress usually generate or give out sound waves in the order of 2 megahertz or higher and not 20 megahertz. In this acoustic emission based detection technique, you can also detect the location of the crack by triangulation technique. And this acoustic emission signal can be a continuous signal or can be just transient or burst type of signals. and you can estimate the Q factor from the peak frequency and the frequencies at which the amplitude drops to 0.707, which is basically 1 by square root 2, basically 1 by square root 2 of the amplitude as frequency by f2 minus f1, and the damping factor and the frequency are also related, so Q factor. So if you know the Q factor, you can estimate the damping factor. And if you are using a bank test, you can actually determine the natural frequency, and in the bank test you actually the system gets excited at a wide range of frequencies, so the amplitude will be maximum at its natural frequency, and that's how you can estimate the natural frequency. In experimental model analysis, you actually measure the force as well as the response or the displacement or vibrations. Both are measured in the experimental model analysis. And mechanical impedance, the opposite is, or the inverse is mobility, and compliance means displacement by force, and the stiffness is force by displacement. So each of them are inverse to each other, compliance and stiffness. And for impedance, mobility is the inverse. And node points are the in vibrating structures are the cases where the amplitude of the vibration is actually zero, perfectly zero. Such points are called the node points. And in the instrumented hammer, there is a force transducer only, and there is no vibration transducer. So you need to have one more vibration sensor if you are using instrumented hammer for experimental model analysis. And in X-ray radiography, the principle is the intensity of the transmitted beam is inversely proportional to the density. So you can see we differentiate bones from the muscles. In similar fashion, you can distinguish different features, or you can define the cracks also. That is it for the today's session. We'll meet again next Saturday. Thank you.